Good day, ladies and gentlemen. Welcome to the presentation entitled Methodologies for the Design of Millimetre-wave and Terahertz Integrated Circuits and LNA Case Study. My name is Božanić, and the co-author of this paper is Professor Sinha. Here is the agenda of today's presentation. I will not go into detail of this. So, I will begin with the introduction. We are at the beginning of 2020. This is the age in which everybody and everything is connected. We have computers, smartphones, wearables connecting to the internet. We have a lot of devices belonging to what we call the Internet of Things or IoT. And then we have the fourth industrial revolution with all the industry components that are also aiming to connect to the network. So we are at the stage where we're actually moving from the concept of where connectivity is something that's nice to have to something that's actually becoming a need. And as a consequence of this, we have the amount of traffic, I'm speaking about the internet traffic, that's increasing exponentially. If you look at this graph at the bottom of the slide, you can see that at present we are sitting at the traffic of, I would say, less than 100 exabytes per month, but this traffic is going to increase to more than 5,000 exabytes, that's 5 zettabytes per month. And what can we do to actually cater for this traffic? Well, we are introducing the new generations of wireless networks. I'm speaking about 5G that's currently busy being deployed, and I'm also speaking of 6G, which is going to be deployed in about 2030. And those are the technologies that will be deployed, or the networks that will be deployed to cater for this increase in traffic. But the question is, how will these networks be able to support so much traffic? Well, the answer is to move to millimetre-wave frequencies and terahertz frequencies. In other words, we need to move to high frequency bands. So for 5G, which is, as I said, going to be deployed or is getting deployed at the moment, we will use millimetre-wave frequencies. Those are the frequencies between 30 gigahertz and 300 gigahertz. And for 6G, which is going to be deployed in about 10 years from now, we will also consider using terahertz waves. And those are the frequencies that start at 300 gigahertz and go all the way up to 3 terahertz, as one can see in this frequency spectrum at the top of the slide. So the main advantage of something like this, of moving to higher frequencies, is that we'll be able to access channels with multi-gigahertz bandwidth. So on the right hand side of this slide, I have a table with some millimeter wave and sub-millimeter wave or terahertz channels, and to the right I have the bandwidth of these channels. And as one can see, more or less the higher we go in frequency, the bandwidth of the channel becomes bigger. So in 5G, we'll be able to utilize, according to the mapping that I'm doing here, channels up to 36 gigahertz. And if we go to terahertz waves, and even if we don't even go above 2 terahertz, we'll be able to get channels in excess of 150 gigahertz. So the question is, what's actually stopping us from doing that? Well, there is a number of challenges. The first is millimeter waves and terahertz waves propagate with the line of sight only. These channels that are talked about now are high attenuation channels. In other words, the signal strength deteriorates as the signal travels through air. Therefore, only short distances really can be reached in this fashion. And at the moment, we still don't have technologies that can actually go all the way up to 2 terahertz, as I have on this table on the right. Rather, we can really only feasibly access the channels up to maybe 100 gigahertz or 150 gigahertz, as I will explain a bit later. And when it comes to that, we don't even have a set of methodologies of designing transceivers that will actually be able to use these channels. Here is the list of challenges that need to be overcome for transmission in millimeter wave and terahertz frequency regime. The first challenge had to do with the channels and the unfavorable channel characteristics. And there are a few ways to overcome these challenges. In each channel there are some low attenuation windows that can be used. Then channels can be crossed with using high gain antennas, much higher than what's currently used. And then we can use more powerful transmitters and use sensitive receivers to get a fairly decent range that we can work with. When it comes to active device technologies, as we start commercially using millimeter wave and terahertz frequencies, we will also continue the research towards improving transitional frequency FT and Fmax of technologies that we have at our disposal. Currently, we have silicon by CMOS technologies that can reach 0.7 terahertz, but we can only really design circuits that that need to operate at frequency up to about half of the maximum frequency. So silicon by CMOS can probably, circuits in this technology can probably be designed up to say 300 gigahertz, maybe even less, 150 gigahertz, as I mentioned earlier. We have some technologies that are very expensive, for example the indium phosphate technology that can that has Fmax that surpasses 1 terahertz, so that can alternatively be used. Then for some other scenarios we can use different technologies, for example gallium nitride for high power, silicon carbide for high temperature, and there is also a technique for that we call silicon on isolator or SOI, which can be used for radiation hardening, for example, but also has many other advantages. When it comes to packaging, we can also deploy different strategies. We can either aim for maximum integration, and then we have the concept that's called silicon on chip, or we can aim for very high quality integration of high quality passives together with die that support transistors with high frequencies, and then we have a hybrid solution, something that we call silicon on package. That's another approach. And then lastly, the last challenge is how do we develop methodologies for the design, because currently, like I said, this is designing in millimeter wave frequencies or terahertz frequencies in art. Well, at this stage, with the improvement in active device technologies, improvements in packaging, we can start looking at reintroducing flow in the design. I want to first look at active device technologies. I have 2 slides on this. In this slide, there is a comparison between different technologies and the performance in terms of cost, power, noise, linearity, and integration capability of all of these technologies. One can look at this table in their own time. In this slide, I look at, again, active device technologies, but from a different perspective. I look at the cost and the availability of models for the design using these technologies. And here we find that we have usually good models for HBT technologies, heterojunction bipolar transistors, and we have silicon by CMOS technology or HBT that also costs, that's also relatively inexpensive. So one must, but at the same time, aim at low cost technologies, but also look at availability of the models before choosing a specific technology. In this slide, we discuss the packaging of devices. I previously mentioned silicon on chip and silicon on package. We can also have discrete components and multiple dies bonded on the same board, and each comes with some advantages or disadvantages. For example, the integrated circuit itself for the silicon on chip has the highest level of integration. It's small, it's inexpensive, but there is a possibility for thermal issues and passives that can be integrated on a chip have low quality. If we go to silicon on package, we compromise the cost for the availability of moderate to high quality passives, but the IC is also larger. There could be potentially high production costs. We could potentially have issues with modeling and simulation, and we could have reliability and yield considerations. And then if we go to a discrete implementation, we can have the highest possible quality passives. Components are readily available, but these systems are large, have high component variation, they have low density, they're very expensive, and most importantly, they are not very suitable for high frequencies. I now want to talk about the methodology for the design at millimeter wave frequencies. And I use the concept of a low noise amplifier to illustrate how a systematic approach can be utilized towards the design, despite the fact that we're now working at much higher frequencies than was previously the case, maybe with some other wireless networks like 3G and 4G and so on. So on the left there's a block diagram of a low noise amplifier. The purpose of a low noise amplifier is to take an input noisy signal and to amplify it while adding a very minute amount of additional noise. The low noise amplifier is characterized by a noise figure. This figure needs to be as low as possible. On the right hand side, I have a schematic of a low noise amplifier. It's a transistor, either a common source transistor or a Cascode combination of two transistors. That's the active device. Of course, this transistor can also be an HBT. We just use the MOSFET symbol in this example. And there's some additional circuitry. So the most important component is the input matching network that's used to do a simultaneous noise and impedance matching. That is the most important component of an LNA. And to aid with this input matching, we could add a source degeneration network, we could add a feedback network, and then we still need the output matching network that's to connect to the next LNA stage or the next amplifier and next component in the receiver chain, and we could have an RFC to decouple the supply. Here I have an example of several LNA technologies. I have a Cascode LNA on the left, in the middle I have a feedback LNA, and on the right I have a multi-stage LNA, which is really a combination of different other stages. The Cascode LNA on the left is a narrowband configuration and has a source degeneration, or in this case the emitter degeneration inductor, and also has a base degeneration inductor. The input matching network is a base inductor. We have a resonant tank in the output signal path. So because of the presence of the resonant tank, this configuration is narrowband. Then we have this feedback configuration in the middle, which is a wideband configuration. The input impedance matching is accomplished with the aid of feedback transistor RF, and then we use the transistor RL for gain. And then on the right we have the multi-stage network, which is typically used as the frequencies increase. It becomes really difficult to use a single stage to both give the simultaneous input match and to give enough gain. So in something like a multi-stage LNA, we would have the input matching network, which would not necessarily input matching stage, which will not give enough gain. So then we would match that to the second and third stage to compensate for that. So this configuration will have a couple of wideband interstage matching networks, a wideband output matching network, and like I said, the input matching network that's for simultaneous noise and power match. This slide shows the step-by-step methodology for the design of LNAs in general. So based on the frequency of operation, cost implication, other implications such as linearity, system integration requirements, environmental consideration, whether we need operation in radioactive environments, in very hot environments, and so on, we can choose the IC technology. That's step number 1. The step number 2, we need to choose the adequate package for the LNA implementation, and that's typically the choice between silicon on chip and silicon on package. The next step, step number 3, is to choose a specific LNA topology based on the frequency of operation. We can decide on the number of stages, and we can decide on whether we are looking for a narrowband or a wideband configuration. And then the last step is to execute the topology-specific design procedure. So once the topology is selected, a few additional steps are required to complete the LNA design. This is typically done with the aid of simulation. This is now dissected in this slide. So step 4 in the previous slide is now dissected into 4 different steps here. We assume now that we picked up the single stage Cascode LNA. If you remember, about 3 slides ago, there was a single stage Cascode LNA on the left. We take that configuration and then we do following 4 steps. In the first step, we use a simulation to size the transistor Q1 for the minimum achievable noise figure. Then, once we have the minimum achievable noise figure in theory, we need to size the components to get it. The first is to size the inductor LE to get the optimum impedance match for noise, and that's done with a real part of equation 1, also a couple of slides ago. And then the second step is to use the imaginary part of that same equation to size the inductance LB in order for it to resonate with a combination of LE and C-pi, which is the input capacitor in the small signal model of the driving transistor, of the drive transistor. Then the next step, step number 3, is to size the Cascode transistor Q2 to optimize for gain and linearity. So now we have the impedance match and we have gain. And then the last step is to design the output matching network for the optimum power transfer. Which brings me to the conclusion. In the past, millimetre-wave and terahertz design was considered an art, and unorthodox methods were required to produce satisfactory performance, to produce satisfactory results when it comes to performance of various blocks. However, as the technology continued scaling, and with all the recent advances in IC packaging, the performance of transistor and the performance of the package is satisfactory enough that we can reintroduce the structure into the design procedure of millimetre-wave and terahertz transceiver blocks. At this stage, we really can only introduce structure at millimetre waves, but we expect in 5 to 10 years we will have even better technologies, even better ways of packaging, so that we can get to even terahertz frequency operation, design for operation in a structured manner. And then in summary, the methodology for millimetre-wave circuits, which can probably be expanded to terahertz circuits in a few years, will consist of choosing the right technology for the application, choosing the right packaging approach, choosing the specific LNA topology, and then a structured LNA component design for this chosen technology. 4 steps. We must note that this methodology can be adapted to any millimetre-wave circuit subsystem. This could be a power amplifier, an oscillator, or mixer, but the point is a structured approach similar to what was described in the context of LNA can be found for these components as well. Thank you very much for listening to this presentation.